quarters of the year last year, if I asked you what the force of gravity was, you said it was mg. Sound familiar? You never really needed to know much about the force of gravity. Very seldom did you actually have to do something like this to determine the force of gravity, did you? For the most part, we simply dealt with the weight. For an object that was near the surface of the Earth, we just multiplied by g, that it would scale whatever the value of the mass was. And it was fortunate because oftentimes the mass of an object never mattered. Did you notice that a lot last year? Now, the reason for that, and for anybody who studied a year of physics knows that the reason for that is because inertial mass and gravitational mass are the same thing. That's why that it often happened that they would cancel out. That won't happen very much in here, by the way. The force that acts on a particle is from something other than the particle's mass. It's from its charge. And therefore its inertial mass is still there and has to be dealt with. So you'll find that mass doesn't cancel out here, ever. At the same time, it was really easy to figure out the force of gravity, though. We just multiplied by g. And the reason is because the gravitational field was g near the surface of the Earth. Everywhere around the surface of the Earth, we called it the acceleration of gravity. But the truth is, g represented the gravitational field. It was a polite construct that allowed us to compute the weight of objects without knowing very much about the actual force of gravity. The electric field is going to be similar, albeit not as convenient. Part of the reason why the gravitational field was convenient to use is because g ended up being an acceleration. That was convenient. And so we called it the acceleration of gravity. But what we were actually doing all the time was recognizing that the force of gravity might be different for different objects, but they all behaved the same way near the surface of the Earth. We're going to turn that idea slightly backwards by defining the electric field. We never defined the gravitational field last year. We're going to define the electric field. And unfortunately for you, the electric field has very circular definitions. The electric field is defined as the force experienced by a charged particle in space divided by the value of that charge. Say it again. The electric field in space is defined as the force experienced by a charged particle in space divided by that particle's own charge. Which means the electric field is in units of newtons per coulomb. Now, if we apply the same idea to the gravitational field, it would have been the force of gravity divided by the object's mass, which is why g was in meters per second squared, because it was newtons divided by kilograms, which is why we called it the acceleration of gravity. But it was actually the gravitational field. It always was. We don't get that kind of convenient collapsing of the units here. Newtons per coulomb is the unit of electric field. And we're going to have two units for this. This is the first one. In a month's time, we'll have another one called volts per meter. For the time being, it's newtons per coulomb. The electric field is a vector. It points in the direction of the force. More importantly, an electric field points in the direction a positive charge would be pushed. Again, the electric field points in the direction that a positive particle would be pushed. Which means negative charges go against the field. Now, here's where it just gets really circular. To calculate the electric field, Step one is to calculate the force on a test charge. Then step two, seems ridiculous, but to find the value of the electric field, we calculate the force on a charged particle, and then we divide by that particle's charge. So the electric field as a construct still requires that you find the force. But we're talking about the force on a test charge. The test charge doesn't actually exist. The test charge is a construct that we create to help us figure out the value of the electric field. I'm going to demonstrate this, but in the beginning, this just feels like an exercise in futility. But there is a reason why we create this construct, and I'm hoping I'll make it to the reason by the end of class. Consider a single positive charge existing in free space on its own. If I bring a small positive test charge close, I know that my small positive test charge is going to experience a force in this direction. The size of this force, not a surprise. And the direction of this force, based on where my test charge is, to the right. Now, a quick observation of what we just suggested is that the electric field at this point would be whatever the value of the force was divided by the value of the point charge. So I would say that at this location in space, there exists an electric field of this size. And that electric field would be directed away from my central charge. Now, I could place my point charge lots of places around. And in each case, I could begin to build kind of a map of what the electric field might look like in regions around my test charge. This map would eventually give me kind of a pattern for what an electric field might look like in all the areas of space around my point charge. So that I might, in the end, come to understand that the area surrounding a single charge probably has an electric field that looks like this. Where the lines are more concentrated, the electric field is stronger. Where the lines are more spread out, the electric field is weaker. Yeah?
How did you get to that equation? Q K R squared for the electric field.
Well, the force on my that was the force, right?
Yeah. Okay.
Does that make sense?
Yeah.
So the electric field serves two distinct purposes. One is qualitative. Moving the test charge around in a region of space should give us a map of what an electric field would look like. Kind of a visual picture of what the space looks like. actual value in the electric field and knowing the electric field isn't in the electric field itself. What I have here actually is electric field around the point charge. You recognize that no matter where I place my point charge, this is what the electric field around that point charge would look like. But it also means that from now on, when I know the electric field, I can figure out the force on any charged particle placed at that location, because I have an expression for the electric field. What I mean is, I don't have to know the force of gravity on any of you. I can tell you what the acceleration of gravity is at a place on the Earth, and you all could compute your own weight. All you would need to know is what the mass placed there is. In places on the Earth, we tend to think that the acceleration of gravity has more value than knowing your weight. I don't need to know your weight to figure out how fast you would fall, right? I know the acceleration of gravity. The electric field serves the same construct. And the reason we use the electric field is it tells us about the place in space, often because we don't actually know what kind of charges are going to be placed there. I want you to think of a battery. If you've ever held a battery in your hand, like a AA or a AAA, does it tell you how much energy is in the battery? And if you have a battery, you can look at it, pass it around. But there's nothing on there about how much energy is in the battery. What is stated on the battery is its voltage. It's 1.5 volts is a common AAA or AA battery, which still doesn't tell you how much energy there is. A battery never tells you how many electrons it can move. They don't give you that information. The battery tells you the voltage. What it's really providing for you is how much of an electric field it can apply inside a wire. That's what the battery tells you. That's what the voltage is trying to tell you. It doesn't tell you how many electrons it will move, but it will tell you how much force it will apply to the amount of charge you supply to it. That's what the electric field gives us. It gives us a manner and understanding how much force would be applied should you place a charge there. So you bring the charge, I'll tell you how much force there is. We study the electric field because we often don't have tangible information for how many charges are actually going to be moved. So we study the electric field instead. What we have done actually in electronics is we have created an elaborate way of never knowing how much charge actually is being moved, because we didn't know what the charges were. So you're going to find that almost all of our initial definitions are all things that are in terms of unit charge. Going into the future, electric field is force per charge. Electric potential is work or energy per charge. Meaning we spend a lot of time having everything in terms of a value because we can never figure out how much charge there actually is. So instead of talking about the work done in lifting something, we will talk about the work done in terms of the work per unit charge. That's the future. That's where we're going because we never know how much charge there is. So you might wonder, well, why do we study the electric field? Why do we talk about the electric field so much? Charges create electric fields. Electric fields affect other charges. We believe that the electric field is the method by which force gets communicated between charged particles. We will use the concept of the electric field as a way of picturing what the space looks like around charged particles. And not just charged particles. Remember the uniform bar from Friday? What do you think the electric field looks like around this bar? I'll give you hints, and then you figure out the rest. I bet there's electric field that's traveling in a straight line away from the bar at its center. do you think the rest of it looks like? And draw it. It won't surprise you that there's like an electric field this way on the ends, right? What do you think it looks like around the middle? That's the kind of thing I want you to think about. We're going to continue this a little bit tomorrow, but we need to do some practice with the electric field, so that's what we'll do tomorrow.
Isn't particle guns how they're like?
Is we tend to have the ability to shape the electric field. We talked a little bit about this on Friday, that a uniform bar of charge produces a unique electric field around it. By shaping charged particles, we can manipulate the shape of the electric field. For example, it's not particularly hard to make a uniform electric field, a field in which the value of the electric field is constant everywhere in a region of space. Understanding the electric field allows us to instantly know what would happen to a charged particle placed in the location where that electric field exists. I don't think it'd be a surprise that if I had a uniform electric field, then I could figure out the force that that charge experienced. If I can figure out the force that charge experiences, then I can figure out the acceleration of that charge. If I can figure out the acceleration of that charge, it's probably pretty probable I can figure out how much energy that charge gets. I mean, these are things we talk about in mechanics. It's not a far cry from what we have here. If I know the particle is going to accelerate, then I know that by the time it gets over here, it's going to have some velocity. If it has some velocity, it has kinetic energy. If I want to shoot particles out with a certain amount of energy, I can probably tune my electric field to do so. If I need them to go faster, create a stronger electric field. If I need them to go slower, bring the electric field strength down. This is actually something you can make, a particle gun. They're not as exciting as they sound in like video games. A particle gun is just something that shoots electrons around, which can be cool, I guess. That's how all old TVs used to work. They all had an electron gun in them. And it just had a thing that had an electric field in it like this, and it shot electrons. You could build one. It'll take you about, I don't know, an hour to build one. But don't imagine that you're going to be shooting lightning through your garage or something like that. So it just won't happen. For a television to do this, it had to have an electric field that was incredibly strong, incredibly powerful. And most TVs did so by using a voltage. And although this number doesn't mean much, it's big, about 200,000 volts. It's about how much voltage a television would use to accelerate electrons. So unless you can generate that, you're probably not going to get a very interesting electron beam. This is why you should never play with an old television. Does anybody have an old one laying around their house? Like one of those tube ones like in the back of my classroom? If ever you feel like you just want to try something interesting, and decide you're going to take apart a TV to see what's inside because Mr. Shelton told you there's this really cool electron gun in the back, then please let Mr. Shelton be the first one to tell you that that's a great way to get electrocuted.
Can you wear one of those chainmail things?
What's that?
The chainmail protector that people use when they mess with electricity.
I promise if you wear chainmail, you will be unhappy with the results of its level of protection. And if you think, I mean, all you really need to do to protect yourself from a static discharge is just to ground yourself, which means if you've ever worked with electronics, you wear a wrist strap that is grounded. But that's not going to protect you from what's on the back of the television, because you're trying to protect yourself from a static discharge. But the television doesn't have a static buildup. It has a device inside that stores opposing charges. So you will short yourself between the two wires. It will pass through whatever you've placed there. It won't go to ground because it has a negative and positive polarity right next to it, and you're providing a pathway. So no, that's not going to protect you here, and so I would not do it, period. And part of the reason I bring it up at all isn't because I expect you guys to go out there and take apart television. is because even if it's been unplugged for years, old TVs can still have residual charge of 100,000 volts. They were designed to be able to hold that charge for a long period of time purposefully, so they wouldn't draw power all the time. Otherwise, TVs would just be drawing power like incredible amounts. Old televisions were terribly inefficient. New ones, before they went to flat panels, were much more efficient. So if you take, like, if that television has not been plugged in for over a year. You know, last time it was plugged in, well, 6 months ago. So if I was to take apart the back, it's probably still got most of its residual charge. You have to know what to discharge before you do so. And the electric fields are pretty high there, so I stay away from them. If you know, I just wanna make sure you guys don't go home and start taking stuff apart. So, one of the things I want to do real quick, and not because this is hard, but because if I don't do this, you'll say we didn't talk about it, even though this is particularly boring, is I want you to do a couple of just really quick, simple things. I want you to assume we're dealing with an electron here. So electron has a couple of properties, you know what those properties are. For example, you know the electron has a charge of 1.6 times 10 to the negative 19th coulombs. You know it's negative. And you know its mass, because we talked about that, 9.11 times 10 to the negative 31 kilograms. Two pieces of information about the electron that we know. Okay? Some simple problems that tend to deal with the electron. Things that are not hard to do. Question number 1. How strong of an electric field would it take to suspend an electron near the surface of the Earth? It's the kind of problem that shows up on multiple choice. I want you to think about what you would have to do that problem. If you wanted to suspend an electron in an electric field so it wouldn't fall to the ground, what size electric field would you have to do so? And would that electric field point upwards or would it point downwards? So think about it for a minute. See if you can kind of come to grips with what you would have to do. And then maybe you can step me through what the process would be.
What was the question again? I'm sorry.
Size of the electric field to suspend an electron near the surface of the Earth. In what direction would it have to point, up or down? You have 8 minutes. I want this to take 2.
Do you want to use?
I know you guys want to jump to your calculators. Come up with an expression first. It's not hard. Do the expression part first. Because if I ask for the number part, you guys are going to give me 15 different numbers because you're all going to make stupid mistakes with your calculator. So, let's remember that to suspend the particle, the net force has to be 0. The only force that's going to act on the particle. So we have gravity acting on the particle, likely acting what direction? Downwards. So gravity's acting downwards. And how would I compute the gravity on a particle? Still going to be mg. I gave it to you earlier in the class. What's another force that's going to have to act on the particle in order to suspend it? So what direction do I want that force to be? I want the force to be upwards.
Yes.
This would be the electric force, QE. That's it. So we want the net force to be 0, so QE has to equal mg. This is all you have to do. But that also means that the electric field is mg divided by q. Good so far? Would that field point up or would that field point down? The field would have to point down. The electron goes in the opposite direction of the field. So I need my field to point down so the electric force would point up. Now, yeah, you can plug the numbers in here, but you understand the numbers aren't the issue here. And I and I do want to be very critical, the numbers aren't the issue here. Is that there are tons of silly questions like this, and some of the more complicated ones that you tend to see in like your physics books will be things like, we're going to launch electrons into a region of space that has an electric field. At some velocity v. We want the electrons to make it to a point this far away so that they don't strike the, the bottom wall or something. What would be the strength of the electric field here in order for the particles to curve and miss the bottom wall? It might not look like it, but this is a projectile motion problem from last year, where the range is d. To solve this problem, you'll have to remember that the particle is going to experience an acceleration due to due to the force experience from the electric field. And the size of that acceleration is going to look like that. Now that I have the acceleration, I can set up a projectile motion problem. You guys remember those from the good old days?
Nope.
Yeah.
Yes.
They're not great, and the problem is that, they'll surprise it on you, so we'll have to practice little things like this, especially if you're not in mechanics this year. But the kind of electric field problems you tend to see in the beginning of the year tends to be problems that just try to remind us that an electric field is something that you can create, and you can use it to steer particles. So they play around with this concept here of making sure you understand that an electric field applies a force to charged particles. So we spend a little bit of time talking about how to calculate an electric field, but we spend most of our time throughout the rest of the year figuring out how we deal with electric fields. And the reason is we want to be able to steer and push particles around. Eventually, problems that have us figure out stuff about the motion of a charged particle, they're not real, they're just constructed problems. Every textbook's gonna have like 30 or 40 of these. What I need you to understand, I have to come to the realization that what our real goal is going to be is to recognize that in a piece of metal, there are lots of available electrons. If we apply an electric field to a region of space where there are lots of electrons, we can force all of those electrons to begin to move. The construct of the electric field is about how we manipulate and control the flow of charged particles. So again, it's esoteric right now. We calculate the electric field by finding the force on charged particles. The truth is, we can measure electric fields very easily. So creating an electric field to move charges is our goal. We don't necessarily know how many charges, but we definitely know the strength and size of electric fields. So our goal is going to be in the beginning to learn how to calculate an electric field. And we're going to do it the same way as I described in class. We're going to use Coulomb's law on a test charge and then divide away the test charge. That's what we'll do in the beginning. But after about a month, our real goal will be to use electric fields to find other things about space and to move charged particles. That's what we really wish to do.